Hello everyone, my name is Izzy and I'll be going to discuss elementary statistics. This is part of the R programming tutorial. So if you happen to notice that we have statistics here, yeah, it is expected because R programming primarily works with data. And in order for us to process those data, we need to put some sort of statistics. So this topic will discuss basic statistical concept, and how will you apply it in R. So yeah, let's go. So we have to identify what statistics is. Statistics is the practice of turning data into information to identify trends and understand features of population. So yeah, as I've said, we will cover some basic definitions about statistics in this topic, and we will use R to demonstrate the application of these definitions. So there will be recent access given content. So there are two main concepts here. Main components in working with statistics. We have data and information. So one thing that with you cannot practice statistics without data or raw data. So this is the first thing that statistical analysis are faced um, when they do their stuff. So data or raw data, in other words, is the records or observations that make up a sample. So depending on the nature of the intended analysis, this data could be stored in a specialized R object, which is called a data frame. So you will encounter data frame on your previous topics or previous or the previous topics that you're discussing with R. So uh, you have to know how a data frame works as well in order to proceed with this tutorial. Uh, Before we can begin summarizing or modeling our data, however, it is important to clearly identify your available variables. So what are the variables then? So a variable is a characteristic of an individual in a population, the value of which can differ between entities within that population. So you recorded the age, sex, and humor level for a sample of people. So um, these characteristics are your variables. The values measured will differ between individuals. So from the word itself, variable, so it varies. So whenever you get samples from people, um, it will be different responses from people. Variables can take a number of forms, determined by the nature of the variables they may take. So there are different forms of variables. We have numeric variables. It is one A numeric variable is one of whose observations are naturally recorded as numbers. So maybe 1, 2.5, 1/2, and so on. So there are two types of numeric variables. We have continuous and discrete. A continuous variable can be recorded as any value in some interval up to a number of decimals, which technically gives an infinite number of possible values, even if the continuum is restricted in range. So it's infinite. For example, if you're observing a rainfall amount, a value of 15 millimeters would make sense, but so would the value of 15.42135 mm. So any number that you have, so it might be very specific or just rounded off numbers. So any degree of measurement precision gives a valid observation. And we have a discrete variable on the other hand, may take only distinct numeric values. And if the range is restricted, then the number of possible values is finite. For example, if you're observing the number of heads in 20 flips of a coin, only whole numbers would make sense. It will make sense to observe It will not make sense if you observe 15.42135 heads. It's impossible. So the if you're looking if you're observing um, a variable which has a specific conditions, for example, you have to give only the whole numbers. So you only have to give the whole numbers. So that is a discrete variable. Next, we have the categorical variables. So it is also important to consider these variables. So like some discrete variables, categorical variables may take one of the finite number of possibilities. Unlike discrete variables, however, categorical observations are not always recorded as numerical values. So not doesn't always have it doesn't need to have numbers as well. So there are two types of categorical variables. Those that cannot be logically ranked are called nominal. A good example of categorical nominal variable is sex. So we have nominal here, sex. So this cannot be logically ranked. So you cannot rank male or female. Obviously, you cannot rank who is the better sex if it's a male or female. They're all equal. I mean, and we have the ordinal. We have the ordinal categorical variable. So this can be ranked. So this is the opposite of nominal. So you can have the dose of the drug with the possible values low, medium, and high. So once you know what to look for, identifying the so once you were able to know what to look for, identifying the types of variables in a given data set is straightforward. So take the data frame checkwidths, which is available already on the automatically loaded data sets package. So we were now going to the R platform, RGI. So we're going to demonstrate how variable is. So you have to install your our platform GUI in order to test this, and you have to install. You have to when you install R, the datasets package, it's also included in that. And in datasets package, you will have the data frame called check WTS or checkwidths. So now we're going to go through that data frame by putting that name of the data frame in our console. So as you can see, we have checkwidths or check WTS, and when you enter it, you will see a lot of data. But we have to actually yeah, there's a lot of data, but there's a command on R that we can just get the first 5 records of this data set. So this is the code. So we have checkwidths, then 1 to 5 inside of a square bracket. So when you do that, you will retrieve the first 5 records. So so the dataset chickwidths, it comprises of weights of 71 chicks. So as you can see, there's a 71 chicks after 6 weeks based on the type of food provided to them. So you have the weight here and you have the feed here. So horse bean, beans, soybean, sunflower, wheat meal, casein. So now let's take a look at the 2 columns in their entirety as vectors. So we can just get we can just get the variable of the data set. So we just have to call the dataset name, then add the $sign, then put the put the variable name, which is weight, right? So for that, you will see you will only see the weight variable on the dataset chickwidths. So if we are going to if we're going to retrieve only the feed variable, or yeah, the feed, you just call the dataset name again and put feed, and put the $sign and put the variable name, which is feed. So whenever we run that, you will see all of the variables of feed variables for the 71 records in the dataset. So you can also see the levels here, which is case in, horse bean, linseed, meal, soybean, and sunflower. So you can see that there are only, these are the possible values for feeds. So as you can see, weight is a numeric measurement that can fall anywhere on continuum. So it is a numeric continuous variable. The fact that the chicks appears to have rounded or recorded to the nearest gram does not affect the definition, because in reality, the weights can be figured, can be any figure. So feed is clearly a categorical variable because it has only 6 possible outcomes, as you can see on the levels, which aren't numeric. So the absence of any natural or easy identifiable ordering leads to the conclusion that the feed is categorical nominal variable. So it means that it doesn't matter. You cannot rank it. Or I mean, it is not rankable, or you don't need to rank it because it's random. Okay. Now we are going to back to our slide. We are now proceeding to the next concept, which is unvariate and multivariate data. So when discussing or analyzing data related to only one dimension, you're dealing with unvariate data. So for example, the weight variable in the earlier example is unvariate, since each measurement can be expressed with one component, a single number. So when it is necessary to consider data with respect to variables that exist in more than one dimension, your data are considered multivariate. So it means that in order for you to consider the data to be complete something, it needs to have it it needs to have to it needs to have variables uh, or one or two variables in order for the data to be complete. So for example, is that of spatial coordinates, which must be considered in terms at least two components, a horizontal x coordinate and a vertical y coordinate. Okay, so we have discussed that univariate and multivariate data. So let's check that in R. So we have Quakes datasets that also part of the datasets package of the R platform. So we have to go to the R programming again. Where is that? Yeah, we have. So yeah, so we have to call the Quakes package. So there's a lot of data in Quakes package, but we will just have to get the first 5 records, as you can see here on the logic that I'm going to enter. So you can, as you can see, on the Quakes data package, a data set, you have the latitude, longitude, depth, magnitude, and the stations. So these are the variables on the top and the data at the bottom. So this quick dataset is contains observations on 1,000 seismic events recorded off the coast of Fiji. So do you know Fiji, where Fiji is? So Fiji is a Pacific island in yeah, it's a Pacific island. It's pretty near. It's pretty far from the Philippines. So it's the middle of the coast, and it's since it's a Pacific country, there's a lot of earthquakes there, as because obviously they're part of the Ring of Fire. So if you look for the first 5 records on this quake, you will see that there's several strong earthquakes I see on Fiji. So the columns latitude and longitude provide the obviously the latitude and the longitude of the event, where is it located. The depth provides the depth of the event or the depth of the earthquake. So in kilometers, so 5 to 650 kilometers, 42, and we have the magnitude. So the magnitude refers to the magnitude on the Richter scale. The severity the Richter scale is the scale that measures the how strong earthquake is. So if you're interested in spatial dispersion, of these earthquakes, then examining only the latitude or the longitude is rather uninformative. So if you want to see how earthquake is strong, you cannot see it on latitude or longitude. You have to see on the magnitude. I mean, but for the location of the earthquake, it doesn't necessarily make sense if you check for the depth only or the longitude only. You have the latitude, you should see the latitude and longitude that is important to determine the location. So, um, as you can as I can understand here, that magnitude is a univariate variable. So it means that in order to check how strong the earthquake is, you only need to have the magnitude variable. But if you want to determine the location, the exact location of the earthquake is, you have to have the latitude and longitude, and that's make the that variable location variable a multivariate because it consists of two or more variables, and you cannot determine the complete variable if it's only one. So that's how multivariate invariate works. And if you want to, so you can easily plot. So the Quakes dataset consists of 1,000 events. So I don't want to call the Quakes dataset here because it will give you 1,000 records. But if you want to visually check the if you want to visually check this 1,000 events and plot it in a sort of a chart, you have to call this this syntax here. So we have the plot function, and inside the parentheses, you will need to call the sorry, you need to call the dataset name, and so I think this plot yeah. So this plot functionality calls the you need to determine the parameters, different parameters inside the plot function. So we have the first parameter, which is the longitude variable of the quakes data set. So it should be, I guess, the y-axis and sorry, x-axis. The second variable should be the y-axis. Yeah, and which stands for latitude. And the other two parameters here um, is points to the labels of the x-axis, and that's the third parameter. And the last parameter, the fourth one, is the label of the y axis. So let's run this function, and as you can see, this is the result of that syntax. So it gives us the graphical model of the Quakes dataset, which consists of 1,000 events. So as you can see, we have the longitude on the x-axis, and we have the latitude on the y-axis. And you can see those dots here are the events. And as you can see, it plots on the location of each of the locations, which is the consists of latitude and longitude of those quakes. As you can see, we have the longitude label here, and we have the latitude label here, and it was we were able to display it because we put the x lab and y lab parameters from the plot functionality plot function. So yeah, that's how the graphics works. So yeah, we were instead of calling the quakes instead of calling the quakes, we are sorry, instead of calling the quakes dataset in one go, we were plotted it using R, so that we can easily see this dataset visually. Now we're going back to our slides. So another concept that you need to remember on statistics is if the data is actually a parameter for statistics. So we already noted that statistics is this a discipline concerned with understanding feature of of overall population, defined as an entire collection of individuals or entities of interest. The characteristics of that population are referred to as parameters. So, um, and because researchers are really are able to access relevant data on every single member of the population of our interest, they typically collect a sample of entities to represent the population and record several data from these entities. They may estimate the parameters of interest using the sample data, and those estimates are called statistics. So the key difference between the statistics and the parameter is whether the characteristic refers to a sample you drew your data from or on the wider population. So as you can see on this image here below, it illustrates the mean of this symbol here. I forgot the symbol. Let's see. Greek letters. It is actually the symbol of mu. So the tree mean of mu is a parameter. So with the mean of the mu of a measure for the individuals in the population as the parameter, with the mean of C or X of a sample of individuals are taken from the population as the statistics. So yeah. So yeah, when we gather some data from the population, what we gathered is actually parameter. Once we collected data and we estimate those parameters, we will that will be a statistic. So yeah, that's the one of the basic concepts of so those are the basic concepts on describing the raw data, which is part of um, working with statistics. Now we are going now to the summary of statistics. So yeah, so since we are learned the basic terminologies on the previous section, we will going to calculate some statistics using R. So in this section, we will look at the most common types of statistics used to summarize the different types of variables that we've discussed. So first concept or first types of statistic is the centrality. So we have the mean, the median, and the mode. So if you learn some statistics in your college, in your first years in college or in high school, I mean, you will be able to remember this three concepts of centrality. We have the mean, median, and the mode. So mean, it is considered to be the central balance point of a collection of observation. So let's say we have a set of n numeric measurements labeled in X. So this one, you will find the sample mean of C as follows. So we have to add all of the variables, X variables, divided into n or the number of the variables, and the product of that will be the mean. So as you can see, we have some data here. So we have 2 plus, we have data of, we have data of 2.4, 4.4, 3, 3, 2, 2.2, 2, and 4. We added here that and divided into 8, and the product is 2.825. That's the mean. The median is the middle magnitude of your observation. So if you place your observations in order from smallest to largest, you can find the median by either taking the middle value or finding the mean of two middle values. So that's that's the definition of median. But how will we get the median? So this is pretty complicated based on the computations here, but I'll try to explain that to you. So let's say that the sample that we have on mean will be our sample to get the median as well. So I have an Excel spreadsheet here. So these are the values that we had on the mean earlier. So first thing is we have to arrange them. So let's arrange them into from smallest to largest. So we have 2, 2, 2, no, 2, 2, 2, sorry, 2, 2, 2, 2.2, 3, 3, 4.4, sorry, 4, and 4.4. So yeah, that's how we arrange it. Next, we have to assign them into variable names. So we have x1, x2, x3, x4, x5, x6, x7, x8. So we have 8, right? So we assign the variables into x1 to up to x8. So the third thing is since we have 8 values, which is even, we have to get the 2 middle values in order to get the mean. So what are the 2 middle values then on this 8 numbered data set? Should be 4 and 5, right? So we will get we will get the fourth and the fifth variable, which is 2.2 plus 3 and 3. Add it, divide it into 2, and you will get the mean by that. So that's what I did in the right side. So you have to get the fourth and the fifth variable divided by 2, which is 2.2 plus 3 divided by 2, and the mean is now 2.6. So that's how you get the mean. What if so that's the mean if the number of variables is even. What if the number of variable is odd? So if it's the variable number, if the number of variables is odd, you just need to get the middle variable. So let's go back to no, not that one. Go back to Excel. So for example, we only have 7. We know that. So what will be the middle variable? That will be 4, right? And what is the fourth variable then? That is 2.2. No more computations. Just get the fourth number, and that's the mean. So the mean if the number is odd is 2.2. I hope you get it. So so in simple terms, if you have an even number of variables, just get the 2 middle values, add it and divide it into 2, you will get the mean. But if it's odd, just get the middle value, just get the value of the middle variable, and that's it. Next is mode. Mode is simply the most common observation. So on the same data that we're getting, you just have to get the number of instances in the data set. So yeah, you just have to on that data that we get, you have to get the number of instances or frequency on each observation. So for the data not the data 2, the data value of 2 is occurred 3 times in the data. 2.2, it's only 1 occurrence. There are 2 occurrences or frequencies for the observation 3. So basically just the number of instances on each data sets. So that's the mode. So going back, so mean, we have to compute for the average. So is the simplest term for that. Median is the middle value, and the mode is the number of instances on each values. So how will we get that on R then? So we'll go to R now. It is complicated if you do it in math, using math. That's why we're doing it in R. So for R, what we are going to do is we have to store the observations as numeric vector x data. So let's do that. So we're going to use the same variables that we have and confirm if the mathematical computations that I did earlier is correct in R. So we'll do this logic here. So we have a vector, numeric vector called x data. Add add the values on that numeric vector using the C function, and you can see that's the same numbers that we tested earlier. So we have that. So now we have the numbers on x data numeric vector. Now we have to compute for the statistics, the three summary statistics that we've discussed. So in order to get the mean, you have to enter this logic here. So x dot bar, then compute for the mean. So once we done that, we have to call the x bar. And you will get the mean, which is 2.825, which is the same as with the in the PPT file, in the PowerPoint. Next, we get the median. So in order to get the median, we have to call a variable m and compute for median and call that variable again, since we have already compute that. M bar, and we get 2.6 because that's the we get the middle value, fourth and fifth middle value, then add it, divided into 2, and that's the median. And for the mode, it will be achieved if we were going to create a table. So in order for that to do that, we have to create a variable x tab, then call the table function, and call the data set that we've the numeric vector that we've set up earlier. Then we call the x tab variable. Now we get a table view of the mode. So the most common based on the data set that we have, the mode of the data is 2, because 2 has the most recurrences in the data set. Though this information here clearly shows the mode for a small data set, it is good practice to write code that can automatically identify the most frequent observations for any table. So the mean and the max functions will report the smallest and largest values, with range returning both in vector of length 2. So we need to call the mean and the max functions on the x data. So we have the minimum data that we have is 2, and the maximum data that we have on the set is 4.4, right? And you have to call the range. So the range consists of the highest and the minimum and the maximum numbers in the data set, which is 2.0 or 2 and 4.4. So when we applied it on the table, So when we applied it on the table that we have earlier, and call the max number of the table, we will get 3, which is you see on the table here, is the same value of the range 2. So therefore, you can construct a logical flag vector to get the mode from the table. So this is the formula for that. Then you have to call d bar. Then you have to set up this x tab. X tab equals max x tab. D bar. Call that d variable. So, which considers the 2 and 3. So here 2 is the value and 3 is the frequency of that value. So now let's return to the check WTS dataset and compute for the mean and the median weights of the chicks. So if we're going to get the mean, you use the mean function. You have to get the mean function, then call the datasets and the dataset check width and the weight variable on the dataset, and you get the mean is 261.3099. So that's the average of all the weights in the check width dataset. And if you want to get the median, which is or the middle value, you get 258. So that's the that is the, since we have seven records, so that will be the 36th value in the data sets. So that's the median. So we cannot get the value of the for the Quakes data. We have to get the so let's go to the Quakes data. So we have to get the mode, I guess, for the, you have to get the mode of, you get the occurrences or the mode of the data from the Quakes dataset. So in order to do that, we have to create a table, yes. And so we have the table called qtab, then assign that table to the qtab table variable. Then on the qtab table value, we have to enter this logic. So this means that we have to get the maximum or the data that has the most frequencies. So as you can see, we have 4.5. So the magnitude 4.5 here has 107 occurrences. So 4.5 is our mode because 4.5 has the most number of occurrences. So yeah, that's how we get the mean, median, and mode. Now we're going to the next concept of statistics, which is counts, percentage, and proportions. So in this section, you look at the summary of data that aren't necessarily numeric. It makes little sense. For example, to ask R to compute the mean of categorical variable, but it is sometimes useful to count the number of observations that fall within each category. So these counts or frequencies represent the most elementary summary statistics of categorical data. This uses the same count summary that was necessary for mode calculation in our earlier sample. So again, you can use the table command to obtain the frequencies. Recall, there are 6 feed types making up the diet of chicks in Chickwit's data frame. So getting this factor level count is straightforward as this. So let's go to table. Let's go. So I go back to the R and let's create a table using the feeds on the Chickwits data sets. So as you can see, this the table that was generated using this functionality. You will see the number of frequencies on each of the categories of feeds in the Chickwits dataset. So you can gather more information from these counts by identifying the proportion of observations that fall into each category. This will give you comparable measurements across multiple datasets. So proportion represent the fraction of observations in each category, usually expressed as a decimal number between 0 and 1. So to calculate the proportions, you only need to modify the previous count function by dividing the count or frequency by the total overall sample size. So what we need to do here is to we need to add so we need to modify this numbers here and divide it into the number of chicks in the data set. So I will gonna do that. So we have to enter the syntax. So we still need to call the table and get the number of frequencies on each feed, but we have to divide it to do the number of rows in the number of rows of the rows in the dataset of Chickwits. And once we generate that, you will see the proportions, the number of proportions. So this is basically like if you are dividing the number of frequencies against the number of instances. So for example, we have 12. We have 12 instances of casein, and there are 71 instances of chicks in the dataset, right? So let's try to compute that in the calculator. So I'm going to go calc. So 12 divided by 71 equals to 16,90141. So yeah. So basically accurate. So that's the proportion. So of course you did not do everything associated with counts by table. A simple sum of appropriate logical flag vector can be just as useful. So recall that trues are automatically treated as 1 and false is 0 in any arithmetic treatment of logical structures in R. So such a sum will provide you with desired frequency, but to get the proportion, you will need to divide the total sample size. So furthermore, this is actually equivalent to finding the mean of the logical flag vector. For example, to find the proportion of chicks fed soybean, note that the following tool calculation will give identical results of around 0.197. So these are the logic that was talking about. So this logic sum, get the sorry. So on this value here, you need to get the sum of all of the feeds under the soybean category in Chickwits dataset and divide it to the number of Chickwits. So you get the you will get the value of 0.197, which is the same on the table above. And there's another and the other way in determining the proportion is to use the mean function. So you have to use the mean and get the chickpeas. Since mean is basically giving you the average data. So it's like proportions here is like the average data. So we'll return the same value as the two cases here on the above. So you can also use this approach to calculate the proportions of entities in combined groups, achieved easily through logical operators. The proportion of chicks fed either soybean or horse bean is as follows. So you need to use the mean again, and you have to get only those chicks with feed with soybean or horse bean. Okay, there's another way in getting your proportions using t apply or tapply function, and this is actually the logic for that. Okay, so t apply or tapply function, you have several parameters here, so we have to get the variable on the data set. Then you have to get the index. Then you have to get the fun argument as well. We need to define it actually. And when we run it, you will receive the same value that you have on the first table, or on the table that we ran earlier. So this disposable function is defined with a dummy argument x, which is defined in fun, which you were using to represent the vector of weights in each feed group to which fun applies. Finding the desired proportion is therefore a case of dividing the number of observations in x by the total number of observations. So the last function to note is the round function, which rounds numeric data output to a certain number of decimal places. So since we are receiving this in a very long decimal places, we can use the round function to give us a round off value. So we're going to apply it using the round function and call the table function that we had earlier, and call the digit parameter here, or argument, which should be 3. So it only should return 3 decimal places. So as you can see, once we apply the round function, we only see the values of proportions on 3 decimal places. So if you set this digit 0 here, the output is rounded to the nearest integer, and it is always the default value of digit on the digit variable. Okay, so that's the proportion for you. Where's So again, the counts of frequency represent the most elementary summary statistics of categorical data, which is the number of observations. So we encountered that earlier in the mode, because we're counting the frequencies on each of the data that we have in the data set, and the proportion is the fraction of the observation on each category. So it will be computed based by the number of frequency against the total number of the instances on your dataset, or the number of variables. Yeah. So it should always be the value should be always between the value of 0 1, which is always an integer value. I mean a decimal value. So next concept is quantiles, percentiles, and 5-number summary. So a quantile is a value computed from a collection of numeric measurements that indicates an observation's rank when compared to all other observations. For example, the median. Um, the median itself, it's a quantile. It gives you a value below which half of the measurements lie. So it is called the for a 0.05th quantile. So alternatively, quantiles can be expressed as percentiles. So this is identical as quantile, but on a percent scale of 0 to 100. So how to compute the percentile now? So it should be, you have, in order to compute for the percentile, you have to multiply the quantiles to 100. So for example, so the median is considered as the 0.5 or 0.5th quantile. If you multiply it to 100, so the median is considered as the 50th percentile, right? So there are different number of algorithms can be used to compute quantiles and percentiles. They all work by sorting the observations from smallest to largest and using some form of weighted average to find the numeric value that corresponds to P. But results may vary slightly in other statistical software. So we are going to do that computation of quantile into R, right? So let's go to R again. Where's R? And we're going to use this logic here. So again, we have to, so we're going to use the sample data that we have earlier, and we have to insert it on the x data variable. And now we're going to call the quantile function. So we're going to call the data variable, the data set, then so we takes the data vector. So I'm keep calling it a data set or data variable, but I guess in R it's called data vector. So that will be our first argument or first parameter. Then we follow it by a numeric values applied to prob, giving the quantile of interest. So we will have to, so the quantile of interest here is the 0.8 quantile, or in the percentile is the 80th percentile. Okay, so once we trigger that, so it will give the 80th percentile, which is 3.6 based on the number here. So prob can take a numeric vector of quantile values. So it's always be the 0.08, 0.05. Also, it's between 0 to 1 again. So this is convenient also when multiple quantiles are desired. So we're going to use the same data, x data, data vector. So we need to call the quantile prob, and we need to call the prob argument, and we have to call, so C stands for array, I guess. So we have to set the array values. So we have 0, 0 0.25, 0.5, 0.75, and 1. So these are quantiles. And when we enter that, it will return the percentiles. So 0 percentile is 2, 25 percentile is 2 as well, 0.5, 50 percentile is 2.6, 75th percentile is 3.25, and the 100th percentile is 40. So keep in note that or always remember that the percentile always in percentage, so it always be like whole numbers from 0 to 100. But if it's a quantile, it should only be value ranges from 0 to 1. So it always be a decimal. So the next concept that we're going to look at is the um, 5-number summary. So as yeah, actually the one that you saw on the last one that you saw, it is called the 5-number summary of data. So it comprised of 0 percentile, so the minimum percentile, the 25th, the 50th, the 75th, and the 100th percentile. The 0.25th quantile is referred as the first or lower quantile, and the 0.75th quantile is referred as the third or upper quartile. Also note that the 0.5th quartile of X data is equivalent to the median. So 25th is the first or lower quartile. 75th is the upper third or upper quartile. 0.05th is the median. So the median is the second quartile actually. So first is 20.25th, 50th is the second, 75th is the third. And the maximum value, which is 100, is the fourth quartile. So there are ways to obtain the 5-number summary, as you can see earlier here. This is the one way. This is using quantiles. So when applying to a numeric vector, the summary function also provides these statistics along with mean automatically. So we will use the summary function on the x data vector that we have. So we're just going to call that, and when we run it, you will see the the minimum, which is the 0th percentile, the maximum, which is the 100th percentile. We have the first quartile, which is, and the third quartile, which is the 25th or the 75th quartile. We have the median, which is the 50th quartile, the 0.5th quartile, and the mean, which is the average of the data set. Right. So to look at some samples using real data, so let's compute the lower and upper quartiles, which is the first and third quartile of the weights of the chicks in Chickwit's dataset. So we're going to use the quartile function here to determine those lower and upper quartiles. So we have 25th and 75th quartiles. I mean 0.25 25th or 0.75 quartiles, which is 2.0.5 and 3.3 to 3.5. So this indicates that the 25% of the weights lie at or below 204.5 grams, and the 75% of the weights lie at or below 323.5 grams. So let's also compute for the 5-number summary of the Quakes dataset. So let's do that using the summary variable. So we're going to see the minimum, the maximum, the first, second, and third quartiles. The second, which is the median, and the mean. So you can see. So the minimum magnitude on the dataset is 0.4, and the maximum is 6.4. The 25% of the quakes in the Fiji is at or below 4.4 magnitude, and 75% of the quakes in Fiji lies at or below 4.9. So that is the meaning of the summary data here for the quakes. So yeah, just to recap, so the quantile it is computed as the collection of numeric measurements. So the value of quantile should always be ranges from 0 to 1. So it means it should always be decimal numbers. So 0.25, 0.5, and 0.75 are quantiles. And percentiles are those quantiles that was multiplied to 100%, and it's always on the percent scale. In the five number summary is always consists of the 0, 25th, 50th, 75th, and 100th percentile, which the 0 percentile is the minimum, 25th percentile is the first quartile, 50th percentile is the median, 75th percentile is the third quartile, and the 100 percentile is the maximum. So I hope you understand that concept. It's pretty easy, I guess. So now we go to the next concept, which is spread variance. Which consists of variance, standard deviation, and the interquartile range. So I think it's getting harder and harder as we go along, but I try to explain it. So the measure of centrality that we explored in the earlier section offers a good indication of where numeric measurements are masked, but the mean, median, and mode do nothing to describe how dispersed your data are. So this concept here is measuring the spread. So it's important also to measure the spread of the data so that you can see if there's any outliers or something, or is there any variance and yes, deviation as well. So so in order to get those spread values, we should set up our data first in R. So I'm gonna refresh it first. So X data. So we will create X data data vector, and we're going to have the Y data vector as well. So although these two different collection of numbers, note that they have identical arithmetic mean. So let's check that if we have that same arithmetic mean. Okay, so that's the mean for X data. So for the Y data, so now let's plot these two data vectors side by side, each one on a horizontal line, by executing the following logic. So we're going to execute a lot of logics here. So we're going to plot this first using the plot function. So we have the plot. We don't have that. We use the abline function. That's another abline function here. We also have these texts so that we can also set the labels. And lastly, we have to plot the points. I hope I could able to get a very good view of the data based on the X data and Y data vectors we have. Yeah. So now you get it. So you say how to use this space R graphics in the previous lessons that you have. So we have plot, AB line, text, and points functions. So the resulting graphics on that is this one. Though it should be explained that because some of the observation in X data and in Y data occur more than once, you can randomly alter them slightly to prevent overplotting, which aids in the visual interpretation. This step is known as jittering, and is achieved by passing the numeric vector of interest to the jitter function So we have the jitter function here on the points prior to plotting the points. In addition, note that you can see Yaxt equals to n in any call to plot to suppress the y-axis. Similarly, the bty equals to n removes the typical box that is placed around the plot. So you will focus more on the plot customization on this on the next lectures. So the result, as you can see, provides you a valuable information. So though the mean is the same for both x data and y data, you can easily see that the observations in y data are more spread out than the observations on x data. To quantify spread, you use the values such as variance, standard deviation, and interquartile range. So it is right that you can see that y data is more spread, and X is more compact, but even though they have the same means. So, and you also use the jitter function so that we can able to see um, the plots clearly and avoid overplotting. So you have to remember jitter, and before you plot the points, you have to use jitters and Yax and BTY as well. So let's go back to the spread variables. So we have variance. So the sample variance measures the degree of the spread of numeric observations around the arithmetic mean. The variance is a particular representation of the average squared distance of each observation when compared to the mean. So in order to compute this, for a set of n numeric measurements labeled as x1, x2 up to xn, the sample variance as 2x is given the following, where x is the sample mean described in the previous equation. So our mean here is 2 point what? See, 2.825, right? So this is the mathematical computation of variance, and this is how we compute for the variance based on the data that we have earlier. So this is the computation for the x data vector. So we compute what we did is we we compute for the square we have to square the difference um, of the variables minus the mean and add it and divide it into the number of variables minus 1, and you will receive the variance, which is 0.908. Next, the standard deviation is simply the square root of the variance. So we have computed for the variance, and we just have to use the square root. We have to just find the square root of the variance value. So a rough way to interpret these values is 0.953 represents the average distance of each observation from the mean. So we have the mean that we have is 2.825, and the 0.953 is the average distance of each of the values from the mean. So unlike the variance and standard deviation, the interquartile range is not computed with the respect of sample mean. The IQR, or interquartile range, measured the width of the middle 50% of the data. That is the range of the values that lies within the 25% quartile on the other side of the median. So as such, the IQR is computed at the difference between the upper and the lower quartiles of your data. So formally, where QX denotes the quartile function, the IQR is given as IQR is equals to uh, the value of the 75th the value of the 75th quartile and the minus the value of the 25th quartile. So in R, we can able to compute for IQR directly using the IQR function. So we have, so and also in R, we can actually use, we don't need to compute for variance and standard deviation using the complicated math. We just have to call the var, st, and IQR function in R. So for our x data, we just have to call the var to check the variance, standard deviation, we use st, and IQR, we just use RQR function. Pretty straightforward, right? So we don't need to do complicated math on that. So that's what the magic of the R programming is. So if the based on the x data data vector, the IQR that we have is 1.25. And the var, the variance. So let's see what we have on the. So the variance we have is 9.08, which is actually pretty accurate. It's around off of 9.078501, and the standard deviation is 0.953, which is pretty accurate as well. So yeah, so that's how we are getting it. So you can confirm that the relationship between sample variance and standard deviation using the square root function squared on the result of var, and you can reproduce the IQRs by calculating the difference between the first and the third and first quartiles. So we're as you can see, we're using the basic function to get the var, sd, and IQR. But if you want to be more complicated, we can use other means, like getting the square root from the variance function. So we can add that's the substitute for SD, and we also, and for IQR, instead of using the IQR function, we use this very long functionality, as.numeric, which is the IQR equivalent, the IQR substitute is to minus or get the difference of 25th and the 75th, or the third and the first quartiles, and convert it as a numeric variable, and you will get the same value as the simple RQR function. So as.numeric actually strips away the percentile annotations. So if you're just using this, we are seeing the 75th quartile value, which is should not, right? So we are we use this to remove that 75th percentile value. Now we do the same with the y data. So we are going to get the standard deviation for y data. So st y data. And IQR. Y data. Oh, IQR, sorry. IQR. 1.6. So yeah, that's how we compute variance, ST, and IQR. Those are spread concepts in statistics, or spread calculations, or ways to compute for the spread in statistics. So interquartile. Next concept is the covariance and correlation. When analyzing the data, it is often useful to be able to investigate the relationship between two numeric variables to assess trends. For example, you might expect height and weight observations to have a noticeable positive relationship. Taller people tend to weight more. Conversely, you might imagine that hand span and length of hair would have less of an association. One of the simplest and most common ways such associations are quantified and compared is through the idea of correlation, for which you need the covariance. So, in order to compute for correlation, we have to get the covariance first. So, the covariance expresses how much two numeric variables change together in the nature of the relationship, whether it is a positive or a negative change. Suppose for n individuals, you have a sample of observations for two variables, labeled as x1, x2, or y1, y2, up to yn, or xn, where xi corresponds for yi for 1 equals to 1 up to n. The sample covariance Rxy is computed with the following, where x and y represent the respective sample means of both sets of observations. So this is actually the computation for covariance. So when you get the positive result for Rxy, which is the covariance, it shows that there is a positive linear relationship. So it means that as x increases, y increases. When you get a negative result, it shows a negative linear relationship. So it means that as x increases, y decreases, or vice versa. So when the covariance is equal to 0, it indicates that there is no linear relationship. So as you can see on the right, on the image on the right, we compute the so we compute for the covariance. So we compute for the covariance for between x and y, x data that we have on our previous examples. So we will use the same examples. So as you may note, those two data sets or data vectors both of them have sample means of 2.825. So what we need to do is actually to yeah. So what we need to do is to get the difference between the value of x or what x x data, the values from x data minus the mean times the value from y data minus the mean, and divide it into n, which is the number of the variables on each of the data sets, minus 1, which is, so as you can see here, we compute the first value on the x data minus the mean times the first value of the y data minus the mean, and so on and so forth up to the last one. And we were going to add that all of them and divide it into 7, and the value here is, based on that computation, the value will be 1.479, which is a positive value. It means that as the value of x, which is 2, increases, the value of y increases. Now we able to get the covariance. Now we can get the correlation. So it allows you to interpret the covariance further by identifying both the direction and strength of any association. There are different types of correlation coefficients, but the most common of these is Pearson's product moment correlation coefficient, which is the default coefficient that is implemented by R. So this is the mathematical computation for that. What we are doing is we need to get the covariance, which is 1.479 minus the divided by the divided by what is that? What is 0.953? You know, and I'm gonna check what's where's 953 is. Yeah. Okay. So on this computation, you will compute for to compute for the correlation using the Pearson's product moment correlation of coefficient, we need to get the correlation covariance value divided by the product of the standard deviations from the um, two data vectors, which is the x and y data vectors. We have computed it earlier. So for standard deviation on x, we have the 0.953, and for y it's 2.013. Once we get all of them, the quotient of these the quotient of that is 0.771, and that is correlation. So for correlation, so if the value of the correlation is -1, a perfect negative linear relationship exists. Any result less than 0 shows a negative relationship, and the relationship gets weaker the nearer the 0 the coefficient gets, until it arrives to 0, showing that there's no relationship at all. As the coefficient increases above 0, a positive relationship is shown until um, until the correlation is equal to 1, which is a perfect positive linear relationship. As you can see, the value of correlation here is 0.771, which is standard, which means that the correlation has a positive relationship. So if you take this so yeah, that's correct. So it again 0.771, it indicates a moderate to strong positive association between the observations in x and y. So again, um, that's the correlation of x and y. So we have again we have also commands in R to get the covariance and correlation. So where we will be using the same value that we have earlier. Let's go to R. Where's R? Okay, we have R. Okay. So I will not change the value here, so it's still the same, as you can see. So let's. So in order to get the covariance, we have to use the covariance, the um, call function, and the arguments that we need to enter are the values from the x data vector and y data vector. That we get 1.479286, and which is basically the one that we get on the computation in the part in the presentation. And in order to get the correlation, we have to get the value. We have to call the call function again, divided by the standard deviations from x data times divided by the product of standard deviations of x data and y data, which is 0.771, which is the same in the PowerPoint. So yeah, that's how we compute for covariance and correlation there. And you can actually plot this bivariate observation in a coordinate-based plot or a scatter plot. So executing that will give you this image. Executing this will give you an image. Let's see if we're able to get that. Yeah, able to get that one. Yeah. So plotting the x data and y data observation as bivariate data points illustrate the interpretation of correlation coefficient. See? So plotting in order to do that we need to run the plot function, get the insert the x data, y data on the attributes, PCH. So as discussed earlier, the correlation coefficient estimates the nature of linear relationship between two sets of observations. So if you look at the pattern formed by the points here, and imagine drawing a perfectly straight line that best represents all the points, you can determine the strength of linear association by how close those points are to your line. So points closer to a perfect straight line will have a value of correlation closer to either -1 or 1. The direction is determined by how the line is sloped. An increasing trend with the line sloping upward toward the right indicates positive correlation. And a negative trend should shown by the line sloping downward toward the right. So as you can see here, it's kind of going upwards. See? So it means that we have a positive trend. So considering this, as you can see the estimated correlation coefficient for the data in the plot makes sense according to the previous calculations. The points do appear to increase together as a rough straight line in terms of the values in x data and y data. But this linear association is by no means perfect. How can you compute the ideal or best straight line to fit such data? So it's not actually it's basically as you can see if you're going to draw a straight line, it seems that all of them it seems that the trend here is going up. It's not going down. It's different. So I actually there's some other examples on how we will see the correlation. So as you can see on this data, it displays different scatter plots, each showing 100 points. These observations have been randomly and artificially generated to follow present true values of correlation labeled above each plot. So as you can see here, um, there are some instances here. So as you can see, the if the correlation is um, if the correlation is -1, you can see that it is a perfect downward or negative relationship or negative trend. As you can see on the other negative territories here, um, it's still downward trend, but it's not perfect. But if you see one here, if the correlation is equal to 1, it's a perfect positive trend. Um, as you can see on the bottom here, and on the bottom here, all of this have correlation of 0, meaning there's no correlation at all. So it doesn't necessarily positive or negative trend, or they have no relationship at all. So that's how correlation works and how it can be seen on different plots in R. So let's have another example of correlations. So let's try to check the correlations between on the Quakes dataset. Let's see if we can able to see that. I don't see that. Hmm. Oh yeah, okay. Actually, it's here. So for the Quakes, data set, you can observe that the graphics here are upward trend. Yeah, it means that um, it seems that the correlation is positive. So let's try to determine that if that's the case. So we will use the covariance. We compute for covariance first for the Quakes dataset, which is points 7.0 7.508, which is a positive value, which means that um, as the x or the first variable increases, the second variable increases too. And now we can compute for the correlation. So in the in R, we as you can see earlier, we have computed a lot. Uh, we have computed it using the covariance, but it turns out there's a simple functionality to check to get the correlation. We just need to use the correlation function or core, and you can see that the correlation is 0.85, which is a strong which constitute to a strong sorry which constitutes to a what um which is which means that the correlation is a positive strong positive association between the observation with x and y, meaning that the trend is positive here. You have the positive trend in simpler terms. So yeah, that's how we are getting the correlations and covariance. I mean covariance. How? So in order to get the correlations, just to recap, we need to get the covariance, and the correlation determines if the trend on the data between x and y is positive or negative. If the correlation is -1, it is a perfect negative correlation, and if the correlation is 1 or +1, it's a perfect positive correlation. And if it's a negative, if the correlation is negative, uh, it means that there's a downward trend. If it's a positive, it's a upward trend. It's a positive trend, and yeah, that's and if the correlation is equal to zero, there's no relationship between two variables at all. So yeah, I hope you learn something on that. And lastly is the outliers. So an outlier is an observation that does not appear to fit with the rest of the data. It is noticeably extreme value when compared with the bulk of the data. In other words, an anomaly. In some cases, you might suspect that such an extreme observation has not actually come from same mechanism that generated the other observation. But there's no hard and fast numeric rule as to what constitutes an outlier. It's actually based on the observer's thinking or as the statistician's perspective, I guess. So let's try to get an outlier based on some samples. So let's go to ah let's go to R again. Okay, let's run so let's create another vector called foo and insert a list of numbers or yeah, and let's try to plot it out. So use plot AB line arrows and text. Yeah, let's see if what the product is. Where's that? Here. Yeah. So as you can see here, there's one data here that is an outlier, which is very far from the group of data here on the left side. So that means an outlier. It's very simple. It's with the one is if you can observe if you can compare it with a fairy tale, that is the ugly duckling of the data. Yeah. So I guess that is very simple to identify. If especially if you plot the data and you can achieve it using R. And yeah, that are the concepts that we encountered on our lesson on our topic today. So just to recap, we have mean, we have median, we use tables and mean max range. We can get the minimum maximum, round, quantile, summary, jitter, var and SD, IQR, Cove, and Core for covariance correlation. So these are the R codes that we use for this topic. And there's additional, as you can see, and you must encounter it on your previous topics in your R program tutorial. And that's it. So I hope you learned something about statistics today. I myself is not good at statistics, but able to read and trying to understand this topic has given me a lot of knowledge about statistics, and I hope that I'll be using it in the future, especially or you in the future if you're going to do your thesis, because there will be a lot of statistics for sure in your thesis or in your software project. So I hope you learn a lot, and I hope to see you soon, and thank you so much.